That's from the Oxford book, right?
Yeah.
Okay, okay, all right.
So it says 4-point charges of equal magnitude are held at the corners of a square shown below. The length of each side of the square is 2a, and the sign of the charges is as shown. The point P is at the center of the square. Okay. Determine the magnitude of the electric field strength at point P due to one of the point charges. So we just calculate it by any like 1 point charge, right?
Due to one of the point charges. Yeah, yeah. And they're all the same, so each of them should carry the same magnitude of force, or the same magnitude of electric field, right?
Okay, yeah. So we would use the F equals, oh no, that's for 2 of them. So it would be E equals F over Q, or we don't know F?
Yep, F over Q. And F would be, it would be KQQ over R squared, right?
Mm-hmm. Yeah.
So it would be just KQ over R squared. And if it's KQ over R squared, we just need to find the radius or distance R, right?
Right, and diagonal, so 2a squared plus 2a squared.
Well, it'd be half, or sorry, it's A and A, right? Because it's a distance.
Oh, that's true.
Yeah, right? So it'd be square root of, all right, it would just be A root 2 in the denominator. Squared, right? Because it's, no, is it KQ over R squared, right?
Yes.
Yes, because potential is KQ over R. Yeah, sorry.
2a squared, I guess, in the denominator then?
Yes, yeah, 2a squared in the denominator, and
so K times
KQ over
2a squared.
2a squared, yeah. Let me check that real quick.
So do we just leave it like that?
Yeah, because it's right now, I mean, they're not giving you numerical answers, so that's the only way you can do that. And yes,
like
that's the correct answer.
Like for Q, would we have to like multiply it out, or do we just leave it?
Wait, sorry, say that again. For Q, would we multiply? What do you mean by that?
Sorry, not for Q, for K, since it's KQ over 2a squared.
Okay. I mean, because it's I'm not too sure about IB, but I know for AP, you're allowed to just leave the K because it's recognized. Just like in a problem, sometimes you could say, I know if you had like 10G for like gravitational acceleration, you would probably multiply that out. But if you have like a more complicated answer with just like variables, because you have an A in this problem, you might as well. It's a recognized constant. And in the answer key, they have KQ over 2R.
Even if you put the number, it still means the same thing. So
yeah.
Okay. Second one, on a copy of the diagram above, draw an arrow to represent the direction of the resultant electric field at point P. So I kind of feel like they would all cancel out, but I'm not sure if that is the case.
I would draw the individual ones, just relative magnitude, obviously not exactly, but.
Let's do that. Let me use color. Okay. Well, these two would be attracted to each other, right? Like this one and this one. And so would this one and this one.
That would push that way. It wouldn't be 0 though, because, can I annotate on there? Let me see.
Yeah.
Yeah. So the Q, the plus Q is going away, right? It's going like this. And then the minus Q is also going like this. It's going towards it because, so it's both of them going down that way, down and left. Similarly, you have going this way for this.
Why would the negative Q go down and left? Wouldn't it move up towards the positive one?
Well, it would go up. Remember, we're using a positive test charge, right? The positive test charge would be repelled from the plus Q, which is why it would go down to the left. And if you have a positive test charge at the center, it would go towards the negative charge. So it would so that they would add in that direction. And then same thing. So essentially what we do know is that the horizontal components of the electric field will cancel, right? Because you have.
Okay. So then
now
it would be a net force downwards, like just straight downwards, right?
Yeah, but I think we're doing electric field. So we already found what. I think we already found what the electric field due to just one of the charges is, right?
Yeah.
That was what?
The KQ over 2a squared.
2a squared, right? I think we need to go off of that, right? So now what? Oh, we need to take the vertical component of that, right?
Wait, hold on. I just said, okay, and the next one is, okay, determine the electric field strength.
Oh, yeah, okay. Sorry. Okay, yeah, you're right. It'll just go down.
Okay, so it would be two of those forces in this direction and two of those in this direction. And how would we find the resultant? Like mathematically?
We would have to use well, we have KQ over R squared is just one of them. So we have 1, 2.
We do have these two right triangles here. I don't know if that would help.
Oh yeah, we're gonna have to use sine. We're gonna have to break it up into its vertical component. Yeah. Okay, honestly, what I would do just to get myself from being confused is I would first find the vertical component of just one of them and then multiply by 4. Otherwise, that'll just mess up with my mind. I don't think I would be able to do it the other way.
And it's 45, 45.
Oh, it's a square, right? So yeah, it would be fair.
And the diagonals.
Then we would take sine theta, but we have to define theta. We can't put theta in our final answer because they didn't give theta in the problem. We're gonna make it. So assuming this is theta here, right? If that's theta, then this would be sine theta, right? Not sine theta, sorry. Sine theta would be what?
I'm sorry, is this the angle over here? This one?
Sorry, let me just erase some of the stuff that I drew. Otherwise, it'll get confusing. Okay. Yeah, so what I was saying is if we draw the right triangle here, right, and make this theta, this angle up here theta, then the vertical component should be KQ over 2a squared sine theta, right?
Right, yes, opposite.
Over hypotenuse, and hypotenuse would be that. Okay, so now we have to take 4 of these, right? Because that's the vertical component, and we have to do that 4 times.
Right, so it'd be sine 45 times the 2a squared. Or no, it would just be a square root 2, right?
And then we multiply that by 4 because there's 4 of those forces, right?
Yes, okay.
And then sine, like you said, theta has to be 45 degrees, right? Because it's a square. And P is at the center, or sorry, yeah, point P is at the center. So if that's the case, then sine theta must be root 2 over 2, right? Does that seem right?
Wait, how do we get that?
Oh, because remember you said theta was going to be 45 degrees. So sine theta has to be root 2 over 2.
Okay, yeah.
So then if you do root 2 over 2, then the 4 will cancel with the 4 in the denominator. So we'll be left with root 2 KQ on a squared. Let me check. That makes sense, right? It should be, right?
Yes, I think it should work that way.
Yes. Yeah, the electric field total is root 2 KQ over a squared.
Okay,
good. These are good problems because they're like directly from IB, I think. Like these were on the exams in one or like some of the years, so that's good.
Okay, let's go on to 2. 2-point charges of magnitude 2q and negative q are fixed at the position shown below. Discuss the direction of the electric field due to the 2 charges between A and B. Suggest at which point the electric field is most likely to be 0. Well, I guess it would be most likely to be 0.
I would draw them out again. Like, remember how well we did with them? Like otherwise it's very difficult. It's because it's difficult to visualize all this in your head.
Right, so it would be attracted to this one, right?
Yep.
This one would be more strongly attracted. This one would just be like a little bit attracted. It's farther. And then this one would be repelled like a lot.
Yeah.
And this one would be repelled just a bit.
Uh-huh. And then here you would close to, like over here, you would still be attracted to here, the minus Q, but over time, you would start repelling this way. Why? Because as you get further and further away, it's looking at that as a net plus Q charge, right? Because you have a 2Q and minus Q. So it's
right, yeah.
So somewhere along here, there has to be an electric field of 0, somewhere. Somewhere along here. But I don't know. Sorry, and then here it would be attracted away for sure. So okay, this we know for sure, right? That it's going to be attracted away around point B.
Yeah, definitely.
Between 2Q and B.
Even here, there would be a net like being pushed away, like you said before. So it just, I mean, I guess the net 0 would be somewhere here, right? Because this is where it's closer to negative Q, so it'd be a little bit.
Yeah, and in the middle of Q and in the middle of Q plus 2Q and minus Q, it has to be pointing to the left, right?
Yeah, because it's attracted here and repelled from here, so it has to be from there.
Okay, let me check the answer and see if that's right. It says said at the very left, it says force to the left, which was right. What? This makes no, I can't understand this diagram that they've drawn here.
Do you want to share your screen or something?
Yes, I can do that. Can you enable screen sharing?
Yeah. Should work now.
This is what it says. Wait, did they flip this diagram?
Yeah, I think they did.
I got very confused. I'm like, this doesn't look right.
Yeah, and the other one, negative Q, is on
the left side, right? Yeah, okay. So we said it would have been to the left. Sorry, to the right, very close to minus Q, but then as you get further and further away, it should be, yeah, I don't know what this diagram means, to be honest. I'm very confused what force to the left.
Well, force to the left makes sense because it would be going away from 2Q.
Oh, because that's right. And we said it would have been force to the right over here, right, in this region?
Yeah, and so it says it would be 0 somewhere around the negative Q area. So that makes sense. That's
that makes sense. Okay, that's kind of what we said. Okay. All right. I think our logic was okay. It wasn't bad.
Yeah.
Okay.
Let me get the problems. 2 identical spherical conductors, X and Y, are mounted on insulated stands. X carries a charge, this one. Okay, X carries a charge of 6 nanocoulombs and Y carries a charge of -2 nanocoulombs.
Before y'all do this question, I asked Miss Raja about like spheres and globes earlier, or not spheres, globes earlier, like these kind of questions, and she was like, they're not going to be on the test. You can do it if you want to still just repeat it.
Okay, we could just skip it then.
Yeah, we can skip it. Okay. We can do these on our own time.
Yeah. Is this also, I mean, these are also spheres. So
yeah, I think these are more, yeah, I think the sphere ones we should. You want to try number 5 or no?
Yeah, I think we can do this one.
Okay.
It should be, I don't think we have to calculate anything, so it shouldn't take that long.
Yeah.
Electric fields may be represented by lines of force. The diagram below shows some lines of force. State whether the field strength at A and B is constant, increasing or decreasing, and when measured in direction from A towards B. I would say it's not constant, right? Because it's more dense at A and then it becomes less dense at B.
I'm confused though, because it says the diagram shows lines of force, not, what are lines of force? I've never seen that term before. I don't know what that means.
Yeah, I kind of assumed that it was the field strength lines.
Well, in electric field, isn't the field parallel to the electric force?
The force is...
Force is parallel to the field, yes.
To the field in this, okay.
Okay, so then I think we can kind of consider them, if like, they might not be field lines, but they're kind of, you know, they're along the same lines, so.
So
Yeah, I would say it's decreasing as it goes towards B.
Yeah, I would say it's decreasing as it goes towards B as well. This is number 5, right?
Mm-hmm. Yeah.
At A, it's constant, and at B, it's decreasing. Okay. So I think that's a weird way of saying it, but yeah, that makes sense because the density is, well, of course it's a constant. It's, Yeah. Okay. Yeah, I think we understand it.
Okay. And then 2, explain why field lines can never touch or cross.
That's a good question, conceptually.
Is it because they represent the same field, right? And the same field doesn't really cross on itself.
Okay. If you have two charged particles, right? And they have fields that interact with each other, why can they not cross? Okay, let's suppose that they could cross. Well, what would be an inconsistency then? If they could cross, we know that electric potential is rate of change of, no, electric field is rate of change of potential with respect to time. So
if they cross, wouldn't they produce like an entirely new electric field in a different direction? Because if they're overlapping, then like the strength would be combining, right? At the point where they cross.
I don't know because that doesn't exist, right? So I wouldn't be able to say whether that's.
I don't know. Maybe we can look at the answers.
Yeah, let's see. It says field lines give the direction of the force on a mass or charge. So if lines touched or crossed, particle would move in 2 directions at the same time, and this is okay.
Oh,
so it's like that makes sense. Okay, so it's like it's like if you had like an undefined what is it?
Slope.
Slope. Yes. Yeah. Slope. So it's like if you have like a function, right? And in the function, so if you had like a differential equation that modeled the field, that's like saying you have an undefined. Wait, no, you could have that. Okay, yeah, that's like saying you would have 2 slopes at one spot, and that doesn't make sense. Yeah. Okay.
It's just not possible. Like
it's like we don't think about these things because it's like it doesn't make sense.
Yeah.
Okay.
Okay, this one, 2 insulated metal spheres. I guess we would skip this one.
Yeah, we can skip that.
Okay, now I think we're working with currents. A lamp is at normal brightness when there is a potential difference of 12 volts across its filament and a current in the filament of 0.5 amperes. For the lamp at normal brightness, calculate the power dissipated in the filament and the resistance. Well, the power would just be 6, right?
Yes, I can check, but I'm pretty sure. Yeah, 6 watts.
Resistance is...
I'll make sure you have correct 6. I mean, I know obviously we're just doing this verbally out loud, but just on the exam or whatever, just make sure to put correct. It would be 6.0 if we were to write it down.
Right, yeah. V over I, so that would be 24 ohms.
The overall I, so 12, yeah, I think 24 ohms. Yeah, 24 ohms, yep.
Actually, I just got an ACT passage about this the other day. And it was for me, like... We just studied all this.
I remember when I took the ACT, there was a passage about free fall at like different heights, and we were just learning about that in physics, and I was like, it was just solid.
Yeah. Okay. In order to measure the voltage current characteristics of the lamp, a student sets up the following electrical circuit. State the correct positions of an ideal ammeter and an ideal voltmeter for the characteristics of the lamp to be measured.
Ammeters in series, right?
Yeah.
Okay.
I guess they would put the ammeter like right here, right?
Yeah. Or you could put it after it. It wouldn't matter. Yeah.
Yeah. Or anywhere like here.
Yeah.
And then for the voltmeter, it would be like in series.
Yeah. Like in parallel. Yeah.
Parallel. Yes.
Why is there a variable resistor there? Does that serve a specific function?
I'm not sure.
Okay, let me just see what they did. Oh wait, no. I think which question is this? This is number 6,
it's
right?
6B.
Yeah, that's what they said. Okay, we're right. Series and yeah, ammeter in series, voltmeter in parallel with the lamp.
Okay.
Okay.
So I guess it's just a trick resistor or something. Okay. The voltmeter and the ammeter are connected correctly in the previous circuit. Explain why the potential difference across the lamp cannot be increased to 12 volts. Because there's some internal resistance, right?
The 12 volts battery, so that's 12 volts has to be the EMF, right?
Mm-hmm.
So yeah, so there's some internal resistance, so therefore there has to be, it's the total voltage supplied, the terminal voltage supplied by the battery is less. Yeah, exactly.
Yeah. And it can't be reduced to 0 because no matter how big the resistor is, it would still give some of the voltage here, right? Like it's not going to completely take it away. There would still be like, however small it is, there would still be some voltage.
Yeah, because there has to be internal resistance in the, right, in that. There has to be a potential drop.
Mm-hmm. Yeah.
Yeah, there has to be that, right? Let me see the answers. There must be some resistance in the circuit, some PD. Oh, okay, so for C1, they weren't talking about terminal voltage. They said resistance in the circuit itself. So less than 12 volts is, I do think that the answer about what we said about terminal voltage should work, but I think that their answer is better. Yeah, I think either way should be fine, to be honest.
What did they say?
Oh, what did they say?
Mm-hmm.
Oh, they're saying that it's the internal resistance in the circuit itself, like in the wires.
Oh, that makes sense. Yes.
Yeah, it makes. I think either way would make sense. And then for C2, they said low voltage requires low current and thus large resistance. Max resistance of variable resistor is not infinite.
Is not what?
It says low voltage requires low current and thus large resistance. Max resistance of variable resistor is not infinite.
Wait, how are those two ideas connected?
I think what it's saying is if the lamp had 0 volts, then the variable resistor would have to have 12 volts, right?
Yeah.
Completely.
Mm-hmm.
And if that's the case, then the effective resistance is, or the total resistance is still the same. What are they saying? Low voltage requires low current and thus large resistance.
So if it's okay. So for it to be 0 voltage, it would also have to be 0 current, which means the resistance would have to be infinite, but it doesn't have infinite resistance.
Oh, okay. Well, why is it talking about the variable resistor here in the answer? It's saying, referring to the variable.
Maybe it's just because there is a variable resistor in the circuit.
Okay, but what you said makes sense.
Okay. These problems are harder than the ones that she gave us in the practice.
Oh, they're directly from IV, so.
Okay. An alternative circuit for measuring the VI characteristics uses a potential divider. Draw a circuit that uses a potential divider to enable the VI characteristics of the filament to be found. Okay, I never understood potential dividers, so I do not know how to do this.
So you kind of have to like...
You would draw it onto here, right?
Yeah. Oh, I think that's why they put the variable resistor in there. Okay. Here, let me use annotate. So you would have your, I'm just going to draw a cell. Let's just pretend that's the battery. And you have your circuit, but you have a resistor here, and then that goes all the way here. And then from here, you would have the lamp here, right? Oh, I need space. Here. You would draw the lamp here, and then obviously you still need the ammeter in series with the lamp. Mm-hmm. Then the ammeter would go back into here, and then of course you need the voltmeter here in parallel with the lamp. That would be a potential divider.
Why do we have potential dividers? I don't really get it.
it helps you find the VI characteristics more easily.
Oh, okay.
We can look at the PowerPoint. I think that would clarify it rather than trying to do all this guesswork, right?
Let me.
Because I know I could use some work on it as well.
Okay. Or actually, no, this is not the magnetic one, right? It's the heating effects of currents,
Yeah,
right?
heating effects of currents.
Can you guys see it, or do I need to reshare?
I think I need to reshare.
But let's pass this.
There we go.
Okay, it's a circuit made of 2 or more series resistors that allows us to tap off any voltage we want that is less than the battery voltage.
Okay, we're essentially, okay. We're dividing. So say we only wanted, so say the battery is something like, say that this is 5 volts, and say for whatever machine we're running, we only want 2.5 volts, okay? So if we only want, so I'm just gonna tap it out here by putting whatever new series I want. So let's say I have a lamp here. I'm just gonna put that lamp here and put it in parallel with this so that now it's feeding off of that same potential difference rather than the entire potential difference of the.
Okay, so it makes sense that so this resistor would only get the 2.5 volts, so that means the lamp would get the same.
The lamp would get the same potential.
Okay. Okay, that makes sense. Okay, and the second part, explain why the circuit enables the potential difference across the lamp to be reduced to 0 volts. Wouldn't it still not be able to? Because the first resistor can't have infinite resistance, right?
That first resistor would have finite resistance, but it would have some. Well, it would have all 12 volts going through it, though, right?
The first resistor, yes. Or I mean.
This is dealing with our potential divider, right? So there's only one. We have the main resistor going through, and that has all 12 volts, and we have it in parallel. So if we have all 12 volts, and then we go in parallel here, then the lamp I'm not really sure. Should I look at the answers for that?
Yeah, probably. I mean, I was thinking that it could get like very close to 0, but I don't see how it could be 0.
Okay, here, let me see. It says 12 volts is shared by the 2 halves of the resistor. If the left-hand half has 0 resistance, then the potential difference will be 0. So here. Okay, can I screen share again? Or can you stop? Yeah. Am I screen sharing do you see it?
Yeah, yeah.
Okay. So if this is the circuit with the potential divider, it says 12 volts is shared by the 2 halves of the resistor.
Okay.
So I think it's referring to the variable. So this is what I get confused. I'm not sure how variable resistors exactly work.
Yeah, I don't understand how like the different halves of the resistor could have different resistance if it's within one. I mean, I guess if it was made up of 2 like different.
I think that's how variable resistors work. Yeah, I think that's actually how they work. So shared by the 2 halves of if the left-hand half has 0 resistance. Yeah, so if the left-hand half has 0 resistance, then the potential difference obviously would have to be 0 because it's running through that. Okay. I think I think we would need to learn more about like variable resistors to answer that question, right?
Yeah, I still don't get it.
Yeah.
I'm confused. Wait, also the arrow, like after the emitter, the arrow that's going like directly into the resistor, how does that work?
I think that's like how that's how variable resistors work. Like
okay.
that's yeah. If this were a normal resistor, I don't think you could do that, right?
Okay, cool.
I think
Yeah, because I was like, that's not, you can't just like attach it to the resistor.
Okay, let's come back to this at the end. I think that we could, because I think that would just for our own knowledge, it would help to know how that works. And I'll look in the Oxford book in the meantime.
Okay. Let's go on to the next one. Okay, so this should be like Ohm's law, right? Okay.
Yeah.
The graph below shows the VI characteristic for two 12-volt filament lamps, A and B. Explain why the graphs indicate that these lamps do not obey Ohm's law. I guess it's because it's exponential, right? It's not linear.
Well, I wouldn't say it's exponential because we don't know that for sure. We would have to like prove that. But all you can say is, it's not directly proportional. So because it's not directly proportional, or it's not linear, you can say that.
State and explain which lamp has the greater power dissipation for a potential difference of 12 volts. I guess it would be this one, right?
Yeah, because more.
Yeah.
Exactly. Okay.
The two lamps are now connected in series with a 12-volt battery as shown. State how the current in lamp A compares with that in lamp B. Well, it said that.
Wait, I think that goes to the series though, right? Shouldn't it be the same current if it's in the same, if it's in series?
Oh, that's true.
Right?
Yeah. I always forget, like the voltage distributes, but the current does not.
Yeah.
The same. Okay. Use the VI characteristics of the lamps to deduce the total current from the battery. Okay, so we need to find resistance. What is that? What's it doing? Okay. So V over I, right? So this would be 24 ohms. And then this would be 12 ohms.
I don't think we could do that. I think it would be a good approximation, but the potential drops after the first one, right?
That's true, yeah. But we can't calculate how much it drops without knowing the resistance, so.
I think, maybe you're right. I think we do need to just do what you just did. So you said that the resistance of the first one is how much?
I think this one would be 24, right? 12 over 0.5, and then for B, it would just be 12, so the total is 36. So then it would be 12
I equals V over R. So 12 over 1/3.
12 over 36, so it would be 1/3.
Okay. In the marking scheme, they say the answer has to be between 0.3 amps and 0.5 amps. Each lamp does not have the same PD. Find the current from the graph when the individual PDs sum to 12. Okay, so what we did there wouldn't have worked. I mean, it was kind of an okay approach, but yeah. So then the first one would have been okay, 24. But then once we do that, we would have to say, well, okay. So it's 24.
I think we would have to calculate how much we get from the voltage. But before we can know that, don't we need to calculate the lamp B so we know how much the total resistance is for the current.
Oh my gosh, this seems weird because it seems circular, right?
Yeah.
How would you? Each lamp does not have the same PD. Find the current from the graph where the individual PDs sum to 12 volts. Oh wait, okay.
Maybe it's like where they intersect or something like that on the graph. But that's like 0. It doesn't really intersect anywhere.
The individual potential, the PDs have to sum to 12. Otherwise, it won't work, right? So you could do 12 and 0 doesn't quite make sense.
Do we just
Can you
pick
go
a
back to
number?
the graph?
I mean, how would we, I don't know. How would
Yeah,
we
how would you do that? Can you go back to the
yeah. Okay, let me just start writing stuff down. So we know that for the first one, for lamp A, resistance is 24 ohms. Right, so the current that's going through, oh, but we don't know the current because we have to add the resistance.
Okay, well, yeah. Okay, I think one approach might be, well, you know that lamp A overall is steeper, so its resistance should be higher. So if its resistance is higher, then it should have more potential difference going through it, right?
Mm-hmm.
So I would pick probably a point like this on the graph, something around maybe 4, 6, 8, maybe something around, I just choose this right here, this point right here. That looks like 9 volts to me, and 9 volts and 0.4 amps. Does that look right?
Yes.
And then because we chose 9 here, we would have to choose 3 here. So 2, 3.
But hold on, how can we just like choose numbers like that though? Is that allowed?
Well, we know that whatever it is, it'll add up. So we could, that's why they're accepting a range of values.
Okay.
So then
yeah, that makes sense.
You would choose maybe like something like 3 volts here, and then from 3 volts, you would get 0.5. But that can't be right because you can't have the same.
Oh, but what's the total? What are we finding?
Oh, the total current. So now I guess you would have to find the resistance of the individual batteries at those points.
Yeah, exactly. And then we could find the total current. Okay.
Okay, so 9. Okay, now I need my calculator. Now
so we have 3. So 1 would be 3 over 0.5, right? For
yes.
B, it would be 3 over 0.5. So that's 6. So for B, it would be 6 ohms.
Mm-hmm.
And then for A, it's 9 over 0.4. So 22.5.
I got, oh yeah, and then plus the 6, 28.5 total.
Yeah, 28.
Now I total is V over R, and I get about 0.42. And that's, yeah, that would have been an acceptable answer.
Okay.
That's what, okay, I see what they wanted us to do. Yeah, and whenever they have the graphs, it's very weird sometimes their expectations, so yeah.
Yeah. I hope this one on the test. Okay. Compare the power dissipated by the 2 lamps. Would it be
the same current is running through the 2 lamps, right?
Yeah.
So whichever one has a lower potential difference going through it,
it would be less.
Yeah. So we chose B would have to have less power, I'm thinking.
Yeah.
Yeah, and they just stated it differently. They said lamp A will have greater power dissipation. Okay, and the same reason, because of potential.
How many of these there are? Because I think we're almost out of time. Okay,
let's do some magnetism. Do you want to do some magnetism? Because I feel like that's what the test is.
I think only the last few are magnetism. I was looking at it earlier. Oh, this one kind of confused me. So if we could look at this though.
Sure.
An electron enters a pair of electric and magnetic fields in a vacuum as shown in the diagram.
Okay.
And then it says the question is, it gives you the strength and it says calculate the speed of the electron if the net force acting on it due to the fields is 0. So I was thinking that the force on it by the electric field would be 0 because it's perpendicular, right? So then I wasn't sure how that would affect everything.
I don't think the force by the electric field, why would that be 0?
Because it only has force when it's parallel to the field, or at least somewhat parallel.
But that's for a magnetic field, not for electric. Electric is just normal, right?
I think if it's perpendicular, it doesn't have force. That's what I thought.
That's just for magnetic. For electric field, it's just, remember, it's just Q1, Q2 over R squared. With magnetic field, we deal with the cross product of, that's why it has to be perpendicular.
Okay.
So for for the electric field, the electric force would be upwards, right? Because it's an electron So a negatively charged particle would feel a force upwards.
Yeah.
That means if the B field is pointing, what is that? Into the page? Yeah, that's into the page. So if it's pointing into the page, the magnetic force has to point downwards. Otherwise,
yeah, downwards for this electron.
Downwards.
So they
But
do
it's an
cancel
electron.
out.
So, but it's an electron. So we would have to flip something.
No, it would be downwards because normally if the B field is into the page and the velocity is that way, then it would be upwards. And so if you flip it, it would be downwards.
B field is okay. V cross B. Yeah. So and the magnetic force has to be downwards, right?
Yeah, because we know they cancel out.
Yeah, because they have to cancel out. Okay. All right. So can you go back to the question again?
Yeah, I think we basically just set them equal to each other, the two equations.
Yes.
So
okay.
Electric strength should be F over Q, and then QVB sin 0. And then, do we know? Oh, it's just an electron. Okay, so we can just put that in.
Yeah.
Okay, I think we just have to solve it.
Okay, so I know that electric field equals magnetic field, and the magnetic field equals QVB. We're solving for V, so that means B is equal to E over, oh, sorry, we're solving for V, not B. We know what B is. So we know that V will equal E over QB. And now we can just plug all of these in. So E is what? 3.8.
E is 3.8 times 10 to the power 5.
And then Q is the elementary charge, which is 1.6 times 10 to the minus 19. And then the magnetic field strength is 2.5 times 10 to the minus 2. And I get 9.5 times 10 to the 25. That's quite a fast speed. I don't can that fast.
Yes, we can check it.
The speed of light is 10 to the 8 meters per second. How does that work? Okay, I can check. This is number, what number is this? 17?
17, yeah.
Velocity equals E over B. Oh, darn it. I don't know what I was doing. I missed a, whoops. That's a QE because that's electric force. I forgot to, of course. So now the Q's would cancel. You wouldn't have a Q in the denominator. So it's just E over B.
Oh.
Yeah, I don't know why I put, yeah, the Q's would cancel because I put the electric field equals the magnetic force. Obviously that can't be the case. Okay. So in the denominator, okay, I get 1.52 times 10 to the 1, 2, 3, 4, 5, 6, 7. 1.5 times 10 to the 7. And that is the correct answer.
Great.
Guys, I have like two questions actually. First one is for questions like this, if we were, because you know on some of them sometimes you'll get that the net force acting in some way or another is 0. It would be 0 if the particle was moving perpendicular to the electric field or parallel to the magnetic field, right? In either case, it would be 0.
That's what I thought it'd be, but I think MG was saying that if it's perpendicular to the electric field, it doesn't matter. But I remember a few problems from last time, like from the electric field, like homework. It was like if it was perpendicular, it just ended up having no force because it just doesn't work.
I think you're talking about work.
Yeah,
I think you're talking about work.
Yes,
I don't think you're talking about force. No, yeah. Okay. Let's clarify that because I know that's confusing. So with work is the dot product of force and displacement, right? So if it's force dot displacement, then if the force and the displacement are perpendicular, then that's no work. But in an electric field, remember the electric field, if it's a positive charge, the force is parallel to that electric field because force equals Q times E, right? So
when force and displacement are perpendicular.
Yes, if force and displacement are perpendicular, then your work is 0, but that doesn't have to do with the force. Now in a magnetic field, we're dealing with the force and we're using the velocity cross the magnetic field, and then that force, yeah. So in order to have a maximum magnetic field, magnetic force, maximum magnetic force, V and B have to be perpendicular.
Okay, all right.
It's the force is, the work done is 0 because force will be perpendicular to your displacement.
Okay, that makes sense. And then I have a question on one of I was reading through the is it the Oxford book? What was I? Yes, I was reading through the Oxford book, I think, and I have a question on one of the things that it was showing. Could I screen share that really quickly, and then we
Yeah,
can do
sure.
whatever problems you want with magnetism. It's not like a real problem. It's like a just something that I was looking at and kind of I never understood it when we learned it too. Okay, so can you see it?
Yeah.
Yeah, I can see it.
I don't know. Do you just see my screen? Because I don't know. I can't like.
I just see worked example 4 long straight wires are placed perpendicular.
Yeah.
Okay, yes. So yeah, so this right here, this is confusing for me. Just like this concept.
Okay, let me just read it. 4 long straight wires are placed perpendicular to the plane of the paper at the edges of a square. The same current is in each wire in the direction shown in the diagram. Deduce the direction of the magnetic field at point P in the center of the square.
So you're going to use right-hand rule 2, I believe, right?
Yeah, that's what it says to do, but I'm a little confused on like how.
The current is going into the page, top left corner. So you curl your fingers around and
right,
okay.
it'd be going away, like it says. Like it says that the one pointing towards A, it's going like away from the dot, which makes sense because if it's going into the page, then it would point up like that.
Here, you can imagine drawing concentric circles, right?
Yeah, okay.
And if you end up drawing in concentric circles, it's when it goes around, you can see that the magnetic field is pointing this way. So you would have a field pointing this way.
I see. Okay. That makes sense.
That's how I would do it. Once it's like electric field lines, I would just draw it. Like it's too hard. These things you think you can do them in your mind, but let me tell you, you mess up very easily when that happens. Same thing with B. You can just see why it goes up. C and D, you know that they're here. So once you and they're coming out, so they're coming this way, right? So if you draw, oh my, okay, and then C would be this way, so then D would be, yeah, and then same thing with D, yeah, okay.
Got it. Thank you.
Yeah, no, that was a good question. That's definitely a good conceptual question to think about.
Okay, I think we should just end here. Maybe we already.
Can we do one more problem with magnetism if you have time?
Yeah, sure.
Yeah,
let's do one.
I just wanted to get some more practice with the stuff.
How many? Oh, there's only 3 more, so we could just finish them if you guys have time. Okay. A straight wire lies in a uniform magnetic field as shown. The current in the wire is I, and the wire is at an angle of theta to the magnetic field. The force per unit length on the conductor is F. Determine the magnetic field strength.
The force per unit length? What type of unit is this? And they're using F for that. Oh my gosh. Okay.
So maybe it would just be F over like M, right?
Yeah.
Or like force over M equals F.
Oh my gosh.
And then you would set, or I don't know. Or no, okay, wait. So we have, hold on. We have F equals BIL sine theta. And then you would just do that over M, right? Because it's per unit.
So then the force is MF, right? Because we're saying the F here is force. So, okay, let's look at it like this.
Then would you multiply it? So then when you divide, it would be. Yeah. Or
force equals BI. Oh, okay. Here. Yeah. You were doing this right. Force equals BIL sine theta, and we said that force equals F. The force per unit length. So force divided by meters or length, however you want to write it, L. Right. In this case, we would want to do L because it's going to cancel, right? force over L equals F, right? So we know that force equals FL. So that means that's why I put FM here, but I should have put FL here. So that the left-hand side of that equation is FL. L's will cancel, and you've got F equals BI sine theta, and then B, which is magnetic field strength, you can just isolate, right?
Right. Okay. And I think we just leave it like that, right? Because it didn't give us any values.
Yes.
So just be BI sine theta.
Yeah, if they have numbers in the problem, that's just a calculator business, which I'm not a big fan of because I don't mess it up.
Is that correct?
Let me check. Let's see, this is number 18. FL equals BIL sine theta, rearranging the, yeah, exactly what we did. Perfect.
Great. Okay, 19. A straight wire of length 0.75 meters carries a current of 35 amperes. The wire is at right angles to a magnetic field of strength 0.058. Calculate the force on the wire. Okay, that's pretty simple. That's just plugging in. Do we want to just skip it? I mean,
the formula is just ILB, ILB, and sine theta is, yes, it's just
theta,
ILB. Yeah, skip it. We know how to do that.
Okay, an ion with a charge of 3.2 times 10 to the negative 19 coulombs and a mass of that is moving due south at the speed. It enters a uniform magnetic field directed downwards towards the ground. Determine the force acting on the ion. Well, it is 90 degrees, right? The speed, so V and B are at 90 degrees.
Wait, if they're both... Oh, I'm sorry. I got confused with due south and moving towards the ground. Yeah. Okay. There, yeah, my bad. So how do we want to draw this? So what's south? Do we want to say the plane of the page? So if this is the plane of the page, if this is north, south, west, east.
So south would be like down, I guess. I mean, like...
toward the bottom of the page. Yeah. And then
towards the ground would be like into the page.
Into the page, yeah.
Yeah. Okay, so it would...
That's
so
B.
force would be to the east.
So V cross B.
What's it be?
So sorry, I did this wrong. V cross B into the page. So it would be due east then. Yeah.
Yeah, and it is
positive charge?
Yeah, it's positive.
Okay, due east, that's correct. And then, of course, the force we can just plug in, like you said.
Yeah, and then after that, we would just plug it in. Okay.
In the answer choice, it also asks for the acceleration. I see it doesn't ask for that in the problem, but if we were to do acceleration, then all we do is just do force divided by mass, right? And the direction of the acceleration would be the same because it inherits that.
Right. Okay. Yeah, and it does give the mass. So.
Cool.
Can y'all explain 18 one more time? My sister came in my room and I couldn't hear what you guys said about it.
Oh, that's okay. Okay, so basically, we ended up having, hold on, let me write on this. Okay, so we said that force, I'll just make that like lowercase f. So here it says force per unit length. So we know that the force per unit length is equal to F. That's what it gives us in the problem, right? And we know that the regular equation is F equals BIL sine 0, right, for wires. So we would end up having F over L, or hold on. No, we would have F times L, right? If we multiply both sides by that. So this would cross out here, right? So you know that the force is equal to FL equals BIL sine 0. So then the length, which is L on this side and right? L on the other side, they would cancel out.
Oh, okay.
Then you would just be left with F equals BI sine 0 since the L canceled out. Does that make sense?
Right.
Sine theta, right? Not sine 0.
Sine theta, yes.
Yeah.
Sorry, I was reading it as 0.
Oh, I used to do that. There was another letter I used to do that with. I can't remember. It's the Greek messed me up, but
yeah,
I think we've memorized pretty much all. I think we can. Yeah, I think we can read Greek at this point with all the Greek letters we've been introduced to. All right, is that?
That was pretty good.
I think I'm feeling a little bit better now.
Those are definitely, I think those were probably harder than what we're going to see on the test. So that's good.
And of course, we can always go to the question bank on IB. And you guys have that website, IB?
I think, I don't know.
You're familiar with it?
I think you sent it to us at some point, but I don't think I have it anymore.
Okay.
Do it one more time.
Yeah, if you just search it up, IB question bank on Google or any search engine, it'll pop up, and then you can go on the question bank, click on sciences, physics, and it'll give you every single past problem organized by topic.
Wow.
So it's a very amazing resource.
That's
really
good.
good resource.
Yeah, I was.
Right.
That's why I went to the textbook. I didn't want to do the same problems over again.
Yeah, no, these are good, and especially the ones from the Oxford book. They're really good.
MJ, could you send the answers maybe in the Slack or to me?
Yes, I can. Here's the problem. I have them by chapter, so I can send you the chapter 5. Like, it's too many files to send all at once.
Okay.
Yeah. Do you want the topic 5 ones? I can send them right
just
now.
the ones that we're doing.
Okay. Can we stop recording? I think we're done, right?